Hello everyone, I'm Madam Sheila and today we'll be learning Chapter 5 CPU Scheduling. These are the subtopics that will be covered today. We have basic concepts, scheduling criteria, scheduling algorithms, thread scheduling, multiprocessor scheduling, real-time CPU scheduling, operating systems examples, and algorithm evaluation. So by the end of this chapter, we will be able to achieve all these objectives. The first one is to describe various CPU scheduling algorithms. The second one is assess CPU scheduling algorithms based on scheduling criteria. The third one is to explain the issues related to multiprocessor and multi-core scheduling. And the fourth one is to describe various real-time scheduling algorithms. And the next one is to describe the scheduling algorithms used in the Windows, Linux, and Solaris operating systems. And lastly, to apply modeling and simulations to evaluate CPU scheduling algorithms. Okay, so here we're going to talk about the basic concepts of CPU scheduling. The objective of multiprogramming is to have some process running at all times to maximize CPU utilization. A process is executed until it must wait, typically for the completion of some input-output request. And process execution consists of cycle of CPU and input-output wait. Also, CPU burst is followed by input-output burst. And CPU burst distribution is of main concern. The figure below shows a histogram of CPU burst times. Okay, CPU scheduler. The CPU scheduler selects from among the processes in ready queue and allocates a CPU core to one of them. Queue may be ordered in various ways. CPU scheduling decisions may take place when a process switches from running to waiting state, switches from running to ready state, switches from waiting to ready, and terminates. For situations 1 and 4, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, must be selected for execution. For situations 2 and 3, however, there is a choice. Preemptive and non-preemptive scheduling. When scheduling takes place only under circumstances 1 and 4, the scheduling scheme is non-preemptive. Otherwise, it is preemptive. Under non-preemptive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until it releases it either by terminating or by switching to the waiting state. Virtually all modern operating systems, including Windows, macOS, Linux, and Unix, use preemptive scheduling algorithms. Preemptive scheduling and race conditions. Preemptive scheduling can result in race conditions when data are shared among several processes. Consider the case of two processes that share data. When one process is updating the data, it is preempted so that the second process can run. The second process then tries to read the data, which are in an inconsistent state. This issue will be explored in detail in Chapter 6. Dispatcher. Dispatcher module gives control of the CPU to the process selected by the CPU scheduler. This involves switching contexts, switching to user mode, jumping to the proper location in the user program to restart that program. And dispatch latency is time it takes for the dispatcher to stop one process and start another running. Okay, so here are the scheduling criteria. CPU utilization keeps the CPU as busy as possible. Throughput, hashtag of processes that complete their execution per time unit. Turnaround time is the amount of time to execute a particular process. Waiting time is the amount of time a process has been waiting in the ready queue. Response time is the amount of time it takes from when a request was submitted until the first response is produced. So these are the scheduling algorithm optimization criteria. Maximum CPU utilization, maximum throughput, minimum turnaround time, minimum waiting time, and minimum response time. First come, first served scheduling. Suppose that the processes arrive in the order P1, P2, P3. The Gantt chart for the schedule is like the one below here. And the waiting time for P1 is 27 and average waiting time is 17. Suppose that the processes arrive in the order P2, P3, and P1. The Gantt chart for the schedule is like this, and waiting time for P1 is 3, and average waiting time is also 3. It is much better than the previous case. Convoy effect is a short process behind long process. Consider one CPU bound and many input-output bound processes. Shortest job first scheduling. Associate with each process the length of its net CPU burst. Use these lengths to schedule the process with the shortest time. Shortest job first is optimal. It gives minimum average waiting time for a given set of processes. Preemptive version is called shortest remaining time first. So how do we determine the length of the next CPU burst? You could ask the user or estimate. This is an example of shortest job first. For process 1, the burst time is 6. For process 2, the burst time is 8. For process 3, the burst time is 7. And for process 4, the burst time is 3. And this is the shortest job first scheduling chart. The average waiting time that we can see here is 7. Okay, so how can we determine length of next CPU burst? We can only estimate the length, and it should be similar to the previous one. Then pick process with shortest predicted next CPU burst. It can be done by using the length of previous CPU bursts using exponential averaging. And you can see down here below. And this is the prediction of the length of the next CPU burst. Examples of exponential averaging. Shortest remaining time first scheduling is the preemptive version of shortest job next. Whenever a new process arrives in the ready queue, the decision on which process to schedule next is redone using the shortest job next algorithm. But is shortest remaining time more optimal than shortest job next in terms of the minimum average waiting time for a given set of processes? This is an example of shortest remaining time first. Now we add the concepts of varying arrival times and preemption to the analysis. And this is the preemptive shortest job first Gantt chart. The average waiting time that we can get here is 6.5. Round robin. Each process gets a small unit of CPU time, time quantum, usually 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. If there are n processes in the ready queue and the time quantum is q, then each process gets one n of the CPU time in chunks of at most q time units at once. No process waits more than n minus q minus 1 Q time units. Sorry. A timer interrupts every quantum to schedule next process performance. When Q is large, first in, first out, or first come, first served. When Q is small, it becomes round robin. Note that Q must be large with respect to context switch, otherwise overhead is too high. This is an example of round robin with time quantum. When process 1 burst time is 24, process 2 burst time is 3, and process 3 burst time is also 3. And the Gantt chart looks like this, and typically higher average turnaround than shortest job first, but better response. Quantum should be large compared to context switch time. Q is usually 10 milliseconds to 100 milliseconds. Context switch is less than 10 microseconds. Time quantum and context switch time. Turnaround time varies with the time quantum. 80% of CPU bursts should be shorter than Q. Priority scheduling. A priority number integer is associated with each process. The CPU is allocated to the process with the highest priority, smallest integer, highest priority. There's preemptive and non-preemptive. Shortest job first is priority scheduling, where priority is the inverse of predicted next CPU burst time. Problem is starvation. Low priority processes may never execute, and the solution is aging. As time progresses, increase their priority of the process. This is an example of priority scheduling, and this is the Gantt chart for it. Also, the average waiting time that we can see here is 8.2. This is priority scheduling with round robin. Run the process with the highest priority. Processes with the same priority run round robin. The Gantt chart with time quantum too. You can see here. Multi-level queue. The ready queue consists of multiple queues. Multiple queue scheduler is defined by the following parameters: number of queues, scheduling algorithms for each queue, and the method used to determine which queue a process will enter when that process needs service. Scheduling among the queues. With priority scheduling, have separate queues for each priority. Schedule the process in the highest priority queue. Prioritization is based upon process type. Here we can see from highest priority to the lowest priority. The highest priority here is real-time processes, and then system processes, and then interactive processes, and the lowest is batch processes. Multi-level feedback queue. A process can move between the various queues. Multi-level feedback queue scheduler is defined by the following parameters: number of queues, scheduling algorithms for each queue, method used to determine when to upgrade a process, and method used to determine when to demote a process, and method used to determine which queue a process will enter when the process needs service. And aging can be implemented using multi-level feedback queue. This is an example of multi-level feedback queue. There are three queues here. QO, round robin with time quantum 8 milliseconds, and Q1, round robin, time quantum 16 milliseconds, and Q2, first come first served. Scheduling. When a new process enters QO, which is served in round robin, when it gains CPU, the process receives 8 milliseconds. If it does not finish in 8 milliseconds, the process is moved to Q1. At Q1, job is again served in round robin and receives 16 additional milliseconds. If it still does not complete, it is preempted and moved to Q2. Thread scheduling. Distinction between user-level and kernel-level threads. When threads are supported, threads scheduled, not processes. Many-to-one and many-to-many models, thread library schedules user-level threads to run on lightweight process. It is known as process contention scope, since scheduling computation is within the process, and it's typically done via priority set by a programmer. Kernel thread scheduled onto available CPU is system contention scope and computation among all threads and systems. POSIX thread scheduling. Application programming interface allows specifying either PCS or SES during thread creation. pthread scope process schedules threads using PCS scheduling. pthread scope system schedules threads using SES scheduling, and it can be limited by operating system, like Linux and macOS only allow pthread scope system. This is POSIX thread scheduling application programming interface. Here's some more. Multiple processor scheduling. CPU scheduling is more complex when multiple CPUs are available. Multiprocess can be any of the following architectures: multi-core CPUs, multi-threaded cores, NUMA systems, and heterogeneous multiprocessing. Symmetric multiprocessing is where each processor is self-scheduling. All threads may be in a common ready queue, and each processor may have its own private queue of threads. Recent trend to place multiple processor cores on same physical chip. It's faster and consumes less power. Multiple threads per core is also growing, and it takes advantage of memory stall to make progress on another thread while memory retrieve happens. You can see the figure below. Multi-threaded multi-core system. Each core has more than one hardware thread. If one thread has a memory stall, switch to another thread. You can see the figure below. Multi-threaded multi-core system. Chip multithreading assigns each core multiple hardware threads. Intel refers to this as hyper-threading. On a quad-core system with 2 hardware threads per core, the operating system sees 8 logical processors. There are 2 levels of scheduling. 1. The operating system deciding which software thread to run on a logical CPU. And 2. How each core decides which hardware thread to run on the physical core. Multiple processor scheduling, load balancing. If symmetric multiprocessing need to keep all CPUs loaded for efficiency, load balancing attempts to keep workload evenly distributed. Push migration. Periodic task checks load on each processor, and if found, pushes tasks from overload CPU to other CPUs. Pull migration. Idle processors pulls waiting tasks from busy processor. Processor affinity. When a thread has been running on one processor, the cache contents of that processor stores the memory accesses by that thread. We refer to this as a thread having affinity for a processor. Processor affinity. Load balancing may affect processor affinity as a thread may be moved from one processor to another to balance loads, yet that thread loses the contents of what it had in the cache of the processor it was moved out of. Soft affinity. The operating system attempts to keep a thread running on the same processor, but no guarantees. Hard affinity. It allows a process to specify a set of processors it may run on. NUMA and CPU scheduling. If the operating system is NUMA aware, it will assign memory closest to the CPU the thread is running on. Real-time CPU scheduling, it can present obvious challenges. Soft real-time systems, critical real-time tasks, have the highest priority but no guarantee as to when tasks will be scheduled. Hard real-time systems, task must be serviced by its deadline. Event latency, the amount of time that elapses from when an event occurs to when it is serviced. There are two types of latencies affect performance. Number one, interrupt latency. Time from arrival of interrupt to start of routine that services interrupt. Number two, dispatch latency. Time for schedule to take current process off CPU and switch to another. As you can see here, the interrupt latency. Dispatch latency. Conflict phase of dispatch latency. Number one, preemption of any process running in kernel mode. Number two, release by low priority process of resources needed by high priority processes. Priority-based scheduling. For real-time scheduling, scheduler must support preemptive priority-based scheduling, but it only guarantees soft real-time. For hard real-time, must also provide ability to meet deadlines. Processes have new characteristics like periodic ones require CPU at constant intervals. It has processing time, deadline, and period. You can see down here, the rate of periodic task is 1p. Rate monotonic scheduling. A priority is assigned based on the inverse of its period. Shorter periods means higher priority, longer periods means lower priority, and process 1 is assigned by a higher priority than process 2. Missed deadlines with rate monotonic scheduling. Process 2 misses finishing its deadline at time 80, as you can see the figure below. Earliest deadline for scheduling, also known as EDF. Priorities are assigned according to deadlines. The earlier the deadline, the higher the priority. The later the deadline, the lower the priority, as you can see the figure below. Proportional share scheduling. T-shares are allocated among all processes in the system. An application receives N shares where N is less than T. This ensures each application will receive NT of the total processor time. POSIX real-time scheduling. Application Programming Interface provides functions for managing real-time threads. Defines two scheduling classes for real-time threads. Sketched FIFO. Threads are scheduled using a first come, first served strategy with a first in, first out queue. There is no time slicing for threads of equal priority. Sketched RR, similar to sketched FIFO, except time slicing occurs for threads of equal priority. Defines two functions for getting and setting scheduling policy, as you can see down below. POSIX real-time scheduling application programming interface. Here's more of that. Operating system examples: Linux scheduling, Windows scheduling, and Solaris scheduling. Linux scheduling through version 2.5. Prior to kernel version 2.5, ran variation of standard Unix scheduling algorithm. Version 2.5 moved to constant order scheduling time. Preemptive priority based. It has two priority ranges, time sharing and real time. Real time range from 0 to 99 and nice value from 100 to 140. It maps into global priority with numerical lower values indicating higher priority. higher priority gets larger queue. Task runnable as long as time left in time slice is active. If no time left expired, it is not runnable until all other tasks use their slices. All runnable tasks are tracked in per CPU run queue data structure. Two priority arrays, active and expired. Tasks indexed by priority when no more active arrays are exchanged. It worked well, but poor response times for interactive processes. Linux scheduling in version 2.6.23. It is completely for scheduler. Scheduling classes. Each has specific priority. Scheduler picks highest priority task and highest scheduling class. Rather than quantum based on fixed time allotments, it's based on proportion of CPU time. And two scheduling classes included. Others can be added. Default in real time. Quantum is calculated based on nice value from -20 to +19. Lower value is higher priority. It calculates target latency, interval of time during which task should run at least once. Target latency can increase if, say, number of active tasks increases. CFS scheduler maintains per task virtual runtime in variable vruntime. It is associated with decay factor based on priority of task. Lower priority is higher decay rate. Normal default priority yields virtual runtime, actual runtime. To decide next task to run, scheduler picks task with lowest virtual runtime. CFS performance, you can pause the video and read it yourself. Real-time scheduling according to POSIX 1b. Real-time tasks have static priorities. Real-time plus normal map into global priority scheme. Nice value of -20 maps to global priority 100. Nice value of +19 maps to priority 139. Linux supports load balancing, but is also NUMA aware. Scheduling domain is a set of CPU cores that can be balanced against one another. Domains are organized by what they share, like cache memory. The goal is to keep threads from migrating between domains. Windows scheduling. Windows uses priority-based preemptive scheduling. The highest priority thread runs next. Dispatcher is scheduler, and thread runs until blocks uses time slice preempted by higher priority thread. Real-time threads can preempt non-real-time. 32 level priority scheme. Variable class is 1 to 15. Real-time class is 16 to 31. Priority O is memory management thread and queue for each priority, and if there is no runnable thread, it runs idle thread. Win32 API identifies several priority classes to which a process can belong, and all are variable except real-time. A thread within a given priority class has a relative priority: time critical, highest, above normal, normal, below normal, lowest, and idle. Priority class and relative priority combine to give numeric priority. Base priority is normal within the class. If quantum expires, priority is lowered, but never below base. If wait occurs, priority boosted depending on what was waited for. Foreground window given 3 times priority boost. Windows 7 added user mode scheduling. Applications create and manage threads independent of kernel. For a large number of threads, much more efficient. User mode scheduling schedulers come from programming language libraries like C++, Concurrent Runtime Framework. As you can see here, these are the Windows priorities. Solaris, priority-based scheduling. There are 6 classes available: time sharing, interactive, real-time, system, and fair share, and fixed priority. Given thread can be in one class at a time. Each class has its own scheduling algorithm, and time sharing is multi-level feedback queue, loadable table configurable by sysadmin. Sorry. This is a Solaris dispatch table, and this is Solaris scheduling. Scheduler converts class-specific priorities into a per-thread global priority. Thread with highest priority runs next. It runs until blocks uses time slice and preempted by a higher priority thread. Multiple threads at same priority are selected via round robin. So, how to select a CPU scheduling algorithm for an operating system? Determine the criteria, then evaluate algorithms. Deterministic modeling, type of analytic evaluation, and takes particular predetermined workload and defines the performance of each algorithm for that workload. Deterministic evaluation. For each algorithm, calculate minimum average waiting time. Simple and fast, but requires exact numbers for input, applies only to those inputs. Queuing models describes the arrival of processes and CPU and input-output bursts probabilistically. Commonly exponential and described by mean. Computes average throughput, utilization, waiting time, etc. Computer system is described as network of servers, each with queue of waiting processes, knowing arrival rates and service rates. Computes utilization, average queue length, average wait time, etc. Little's formula, as you can see, you can read it yourself, yeah, I believe. Simulations. Queuing models are limited. Simulations are more accurate. Programmed model of computer system. Clock is a variable, gathers statistics indicating algorithm performance. Data to drive simulation gathered via random number generator according to probabilities, distributions defined mathematically or empirically, and trace tapes record sequences of real events in real systems. This is an evaluation of CPU schedulers by simulation. If you don't understand, you can ask me in class, okay? Implementation. Even simulations have limited accuracy. Just implement new scheduler and test in real times. High cost, high risk. Environments may vary, and most flexible schedulers can be modified per site or per system, or application programming interfaces to modify priorities, but again, environments may vary. So that's the end of chapter 5. Thank you for staying till the end. I'll see you in class. Bye-bye.